In this video, I'm going to go over gears, pulley drives, and sprockets. All right, so these three powertrain elements transfer energy through rotary motion, change the speed of the rotation, they change the direction of the rotation, and they change the amount of torque available to do work. All right, so let's look at the parts of the gear. All right, so these gears are known as spur gears. The circle marked in red shows the outer limit of the teeth. The green circles are known as the pitch circles. The pitch circle of a gear is very important as it is used by engineers to determine the shape of the teeth and the ratio between gears. The pitch of a gear is the distance between any point on one tooth and the same point on the next tooth. The root is the bottom of the gear wheel. The pitch point is the point where gear teeth actually make contact with each other as they rotate. All right, so when we refer to gears, we look at torque instead of work because they rotate in a circular motion. All right, the symbol for torque is the Greek letter case ta. All right, so torque is a measure of how much a force acting on an object causes that object to rotate. Whenever you have a rotation, you're going to basically have a torque. The object rotates about an axis, which we will call the pivot point. The distance from the pivot point to the point where the force acts, or the pitch point, as you saw on the slide before, is called the moment arm and is denoted by an R. So torque, again the Greek letter ta, is equal to the radius times the force. Okay, so torque N equals radius N times force N, or also it can be written as torque out would be radius out times force out. We know that force in has to equal force out. So the torque in divided by the radius in would equal torque out over radius out. I've just rearranged these equations here to set force by itself. So then the gear ratio is the radius out divided by the radius in, or also can be looked at as torque out over torque in when we're trying to find those gear ratios. Okay, so gears can be found in many machines in a workshop or factory, and at home they are often an important part of mechanical devices. In a car, the gears help the driver to increase and decrease speed as he or she changes the gears with the gear stick. The gears opposite are called spur gears because they mesh together. As shown in the figure, gear A is called the driver because it's turned by a motor. As gear A turns, it meshes with gear B and it begins to turn as well. So gear B is called the driven gear. When finding the gear ratio, we can also look at the number of teeth, right? Just like here with it radius out over radius in and torque out over torque in. We can also find the gear ratio by looking at the number of teeth. It would be number of teeth out divided by number of teeth in. So my driven gear here, which is out, is 75 teeth divided by 25 teeth, right, my in gear. And that's equal to 3-to-1 ratio, or just 3 is fine to represent it that way. So gear A has 25 teeth and gear B has 75 teeth. If gear A turns 1 revolution, how many times will gear B turn? Right, so this one goes 1 time around. Gear B then is only going to end up going 1/3 of the way around. So gear A must turn around 3 times for gear B to rotate once. That's where we get the gear ratio then would equal 3. Right, so the gear ratio is equal to the number of turns of the effort gear, driver, necessary to turn the resistance gear, or the driven, 1 time. Right, so which gear revolves the fastest then? Right, if you think if gear A has to turn 3 times when gear B only turns once, then gear A would have to be moving faster. Because when we look at angular velocity, we're looking at number of revolutions divided by time. All right, so let's look at this in a motorcycle wheel turns 3,600 times while being ridden for 6.40 minutes. What is the angular speed of in revolutions per minute? So this letter here is the Greek letter for omega, just so you know. And then so we say number of revolutions, 3,600 revolutions divided by 6.40 minutes is 564 RPMs, which is revolutions per minute. All right, so whenever you see RPM, that's what it stands for. Okay, so how does angular velocity and torque relate? All right, so the power transfer in a rotary device is given by power transfer equals angular velocity times torque. So again, we're going to set it up as power in would be angular velocity in times torque in, and power out would be angular velocity out times torque out. So we know that power in has to equal power out. Set these up equal to each other then. When I rearrange that, notice that our equation, the torque out divided by torque in, that the angular velocity is opposite, because angular velocity and torque are inversely proportionate. So when we speed up a gear, all right, we increase the angular velocity, it means our torque is going to go down. So if we're looking for more torque, we need the gear, the output gear, to be going slower. We need the angular velocity to be less if we're trying to increase the torque. And we can do that by changing those gear ratios, by changing the number of teeth in them. Okay. So here, first let's talk about what each letter means. The variables that you need to know is N is the number of teeth, D is the diameter. Sometimes you'll see an R for radius. Either one works. Right? The omega sign is the angular velocity, and the tau sign is torque. Whenever we look at these, here we're going right to left. The in gear is on the right, the out is on the left. So then we get all of the information that is written on here and put it into its correct places for in and out. All right, so here's the equations that we just talked about. Number of teeth out over number of teeth in, diameter out over diameter in, and we can set all of these equal to each other. So if in a problem I have number of teeth and I have maybe torque out and I'm trying to find out what the torque in would be, or again I have the number of teeth and I know how much torque I put in, I can get torque out by putting them equal to each other because all of these equal the gear ratio. So this particular problem here, where the one on the right is in and the one on the left is out, we can set up our gear ratio. All of these are equal to each other, and as you can tell, they're all equal to 2. We do not have a unit on gear ratio, just like we didn't have it on mechanical advantage, because each of these are going to cancel